So we're going to race through two last topics. All right? One is temperature dependence. We've already seen that as the temperature increases, the rate increases. We know this from chemical reactions, general observations. And the reason for this we can talk about is, but it has to do with molecular energy, right? This idea of impact. Okay, and so it turns out that back in the day, Swedish scientists discovered that the rate constant, as the rate constant gets bigger, the rate goes faster. And so he found that there was a relationship to this. All right? And so it turns out that the rate constant can be calculated from a pre-exponential factor that we call the Arrhenius factor, and knowing the activation energy. We can use the activation energy to relate that back to the rate constant. Now, this isn't a linear relationship, it's an exponential relationship. So, as the activation energy gets higher, it makes the rate constant smaller. But there's a temperature component here. And so, as the temperature goes up, it starts to mitigate this, making the rate constant larger. Right? So, but what's nice about this means that we can plot this. So if we take the natural log of both sides and we rearrange it, we get a relationship like this, allowing us to plot the natural log of the rate constant as a function of temperature. And from that, you can determine the activation energy. It may not seem like much, but this activation energy, this allows us to know something about what's going on at the molecular level. We can actually start to talk about what's happening. It is a chemical quantity that we can't directly measure. If you remember, we can start with this product, we can end with the products, and we can measure that energy different. That's our standard enthalpy calculation or our Gibbs free energy calculation. But this is a transient species. So this reaction takes place, goes through the increases into activation energy, creates what we call an activated complex that is temporary, lasting microseconds, and then it collapses back down into our products and releases that energy back. We can't know what that structure is, but this gives us an idea of what the energy difference is, and we can actually calculate what those structures could be. Right? And so this is one of our first peeks to what's going on at the molecular level. And we started to see some of it with kinetic molecular theory, right, where we're looking at the relationships there. But now we're really starting to see how the molecules themselves are interacting. And all of this goes back to the Arrhenius equation. Right? There are two forms for it. There's this linear form, which we rarely use unless we're plotting. Where we often use it is what we call a two-point form, where we measure the rate constant at two different temperatures, and you are able to calculate the activation energy. This is a simplistic picture. It works better if you do the linear form, but you can still figure this out. General rule of thumb, though, is really simple. All right? For most chemical reactions, the activation energy is less than 100 kilojoules per mole. That activation energy is within most reactions, it's going to be a relatively sensible value. All right? What that means is that every time you raise the temperature about 10 degrees centigrade, it will double the rate of reaction. Right? You raise it 50 degrees, it'll go up by a factor of 16 or 32. And so that's a pretty standard rule of thumb. 10 degrees centigrade, it'll double the rate of reaction. Again, that's a rule of thumb. It's a rough rule of thumb, but it's something to keep in mind. And so if you want to speed up a reaction 5 times as fast, you would have to raise it 20 degrees centigrade, all right, and that would do a good job of speeding it up. Right? Again, you can calculate these values more precisely. But, for you, this is why we have refrigerators, all right? A thing of milk out on the benchtop, out on the counter, if you leave it out for a day, it'll be sour by the end of the day, all right? So, there you go. You drop the temperature inside the fridge, close to 20 degrees centigrade, 30 degrees centigrade, And it slows the reaction down by a factor of 8. So rather than going 8 times as fast, it'll go 8 times as slow, which means that that milk, when it's open, will last for a week in the fridge. All right. So that's because those chemical reactions just go slower. All right. So it's a nice, helpful rule of thumb for thinking about chemical reactions. All right. But we can get at this activation energy. So that activation energy really tells us a lot. The pre-exponential factor, this Arrhenius factor, also tells us that includes some of the collision frequency and the angular dependence of the collisions that are taking place. So there's a lot of information here as well. But extracting that out is something we'll leave to higher order classes. You'll learn a lot more about things like this in physical chemistry. But this is a picture into what's going on at the molecular level. The rate law is a picture of what's going on at the molecular level. Why are some molecules there? Why are some not? We have multiple reactants reacting. Well, the simple answer is it's because it tells us something about what's going on in the reaction, how the reaction actually proceeds. Reactions are molecules smacking into molecules, atoms being transferred, and so, that being said, you can envision simplistic steps, what we call an elementary step, and arrange those elementary steps into something we call the mechanism. So a mechanism is a step-by-step breakdown of what's going on at the molecular level. Right? It is a detailed plan for how the atoms are rearranged. We add up all the individual steps and we get the overall reaction, the balanced chemical reaction. Right? So the balanced chemical reaction doesn't really tell us what's going on. Fire, for instance, CH4 plus O2 goes to water and CO2. There is a huge amount of chemistry. There's hydrogens being transferred. There's oxygens being transferred. And so all those together make up the mechanism. And so we can think of this as a sequence of steps. And each of these steps we can envision, and so they have to make sense. And so this is one of those things you learn about in organic chemistry, in the science of organic chemistry. Organic chemistry, they do this a lot. They tell us about how reactions combine and form. And a lot of the information that they use to determine the mechanism is kinetics. And so they can look at how the kinetic behavior. It turns out that those elementary steps represent something that's going on in the rate law. So for instance, in this one, we have step 1, A and B combining to form C, and then C and B combining to form D. And so the first part of this reaction would be A and B reacting together. And then of course, C would show up in there at the end. But there's no C in this overall reaction, so this C would represent the presence of an intermediate that sort of is long-lived. This is not the transition state, this is an actual intermediate that sort of grows in and then disappears. We see this a lot in chemistry, and particularly in biochemistry. We'll see these intermediates that appear and then are consumed. And sometimes those intermediates are important in other reactions as well. So the material builds up, and then it's recognized that it's built up, and then other chemical pathways turn on. So this is very relevant in biochemistry as well. So a good example of this would be something like the decomposition of NO and oxygen reacting together. NO plus NO2, NO plus NO plus N2O2 loves this lovely brown gas, NO2. And so requires oxygen to be present for this to happen, but the first step is combining of these two molecules to form this N2O2, but that then is consumed. Now you can observe this by looking at the spectra of the gases that are formed. You can see small amounts of this growing in over the time and then it disappearing as it's consumed by the oxygen. Right? So these are intermediates. And they show up in one step and then are consumed in the other. And the net result is they're not there. Okay? And so what's important in these elementary steps is that the molecularity of the elementary reaction is how many molecules are combining. Right? Now, the molecularity has a direct impact on the rate law. All right, so we can talk about unimolecular materials where one molecule is reacting. So, for instance, a molecule falls apart into two species. The rate is going to be dependent on that particular material. So that would be a first order reaction. And you can see the molecularity, the order of the reaction, and reflects the molecularity. For second order reactions where two things combine, they literally have to smack together, that would be second order. And then you can see that as a square term, second order, where both A and A have to combine in some way to form products. They have to react together. So the elementary steps that we talk about often reflect key components of the rate law. But if there's multiple steps, how do we know which one is which? And so it turns out that what matters is the slowest step. Right? The slowest step is the one that controls the rate law. So we can call this the rate determining step. And so when we have a slow step, the rate law is going to closely reflect the reality of that step. All right? When we have a slow step, the reality is going to... And so you can look at these elementary steps and figure that out. So let's take a look at another reaction, H2O2. This is the elephant toothpaste reaction, one that we do. Hydrogen peroxide in the presence of iodine is catalyzed. So adding iodine to hydrogen peroxide really makes it react fast. We can observe that what this does is it transfers an oxygen to the iodine to make an iodide, hypoiodite, and then that hypoiodite reacts with the hydrogen peroxide to form another compound. Right? This step is the slowest step. This one is really fast, and so we can see that it is first order with respect to, there's one molecule of this and one molecule of that, so we'd expect it to be first order with respect to H2O2 and first order with respect to iodine. Okay? Now the iodine doesn't actually show up in the reaction, so the iodine is present at the start and present at the end, and so it drops out. And so what we call this is a catalyst. It is present at the start and it is present at the end, and it enhances the rate of reaction. And so the rate would look like this for this reaction, and it completely reflects the slow step. So this process of determining the mechanism, it's arduous. It can be difficult, and so this is again a big subject of organic chemistry, is talking about how you figure out what the mechanism is in a particular reaction. You propose it, and you see whether it's plausible or not, and then you test it. So oftentimes you have to conduct other experiments for this to be the case. You can look for those IO2 ions or other things and see if you can see them that support your mechanism. Okay. Another way to do this is to look at labels. Right? So a good example of this is hydrolysis of esters, a soap-making process. So you can break the bond here between the carbon and the oxygen, or you can break the bond here between the oxygen and the carbon, both of which produce the same thing, where you take the water and you add the water across this bond or this one. So the trick is which one. So you have to figure out which bond it is. And so one of the things you do is you put in an isotope. We can look at the oxygen label. So you can actually drop in a radioactive water, for instance, and you see that the radioactive water shows up inside the CO2, the carbon dioxide, the acetic acid that's formed in the product. All right? And so this has a role in, shows that the water from outside broke the bond between those two carbons and oxygens and replaced it with its own oxygen. That gives us a clue that this oxygen. So you do a lot of this in biological chemistry, biochemistry, where you're trying to follow reaction pathways. And so you use isotopic labels. O18 happens to be slightly radioactive, and so you're able to follow the radioactive tracer. Now, I already mentioned the catalyst. Catalysts increase the rate of our chemical reaction, even with, and the way they do this is a little bit different. The way they don't react with the products, they don't react with the starting material. They change the energy of the activation's energy by dropping this activation energy. Sometimes they change the shape, sometimes they stretch a bond. They can greatly enhance the rate of reaction. And so this is just a side effect of how the catalysts work. Right? How exactly they do this depends on the catalyst. And so oftentimes they will weaken bonds, they will, or enforce things together in close proximity. So there's a large range of ways they behave. But the net result is they drop the activation energy. They drop the activation energy so much that some of the reactions can become very, very quick. Now, reactions, don't mistake quick for possible. A lot of chemical reactions are thermodynamically, don't necessarily, and changing a catalyst will not necessarily change the thermodynamics of the starting materials and the products, but they do lower this activation energy, making it much readily and more accessible. Big field of interest are heterogeneous and homogeneous catalysts. Heterogeneous catalysts, like in your catalytic converter, they're an active metal surface that's able to split off oxygen molecules. There's a lot of NOx, nitrogen oxide species in your gasoline from incomplete combustion, and so they remove that and help prevent pollution in that way. The active surface splits the molecules at high temperature, and then those recombine to form N2 and O2, which are come out. All right, so that's about, the other are homogeneous catalysts, and probably so heterogeneous catalysts, you know, they are like a surface, they're heterogeneous, they're different phases, but homogeneous catalysts all work in the same phase. Homogeneous catalysts have many advantages, but they're tricky. But biologically, almost all catalysis is homogeneous, and enzymes represent one of these materials. They're able to speed up biological reactions, and by enhancing those biological reactions, they allow us to do things like live. All right, so there you go. And so that's kinetics in a nutshell. Focus on determining rate law, focus on how to extract information from rate laws and use rate laws to measure rates at given concentrations. All right.